Today's FDTD Satellite Applications webinar. Today we're pleased to have Kelly Butler and Chris Jacob from NWS WFO Wichita, Kansas. They're going to be discussing a narrow heavy snowband event that took place. The title of their presentation is Forecasting and Communication Challenges Associated with the February 25, 2020 Narrow Heavy Snowband in Central Kansas. Next slide. Next, we'll just go over some protocol. First of all of these are recorded. If you'd like to check out the recording, that are available on the visit web pages as shown here. If you have something you'd like to share in terms of a future webinar, please let us know, either myself, Dan Bicus, or Scott Lindstrom, and both of us have NOAA.gov email addresses shown here. Next slide. A few protocols to go over. The speakers will have about 20 minutes or so. If you have questions, you can send them via the go-to question or chat. Also, at the end, we'll have a period on the phone where you can ask questions as well. Remember to press hold and mute when you're not speaking. So at this point, I'll turn it over to Kelly.
All right, great, thank you. Good morning, everyone. And so we'll get started here, and here we are. So this is a pretty nice picture here of our snowband that we're discussing that occurred back in February of this year. And this is something we kind of ask ourselves, you know, why do we care about something like this? And so just to try to kind of paint the picture, across in width, this snowband was only anywhere from 8 to 15 miles wide. But in that band, it dropped anywhere from 6 to 13 inches of snow. And all of this occurred over about 4 to 5 hours. And so this is neat, but what about, you know, for all these other areas, the vast majority of people didn't see anything, not even a flake. So why do we care about just this little area of, you know, 10 miles or so? And this is why. So this is a quick summary from one of the Kansas Highway Patrol officers that he created the following day, of just some of the major impacts of something even so small can have such great impacts on us. And we did actually ended up with 2 fatalities out of this event. So we really kind of want to learn what are some tools that we can use in the future to be able to pick up on this, that it's occurring, and also what is the best messaging that we can use to help relay the information to people. So I have just a couple of little loops here of the events. So first off, we had this shield of rain transitioning to snow, and this kind of continued to move pretty good pace east, and right behind that feature is when we see the actual snowband right about here. That's our major snowmaker right there. And if we move on, this is the day cloud phase product from the satellite. And as sun came up, you can see some of the more convective-y natured elements in there. And also, if you look really carefully in the green, that like lime green color, you can actually start to see how narrow of a band we're talking about. And that's something that we can definitely look for in the future. So here is the image, the same image day cloud phase for the next day. So this area here is actually what ended up being our really skinny band, and that's its full extent there. And so I'm just gonna orient this picture a little bit and where we are. So we're up in central Kansas. These 2 water bodies kind of co-located right over here, and north is facing across the snowband. So we're gonna zoom in on this photo and see what we can learn from it. And so obviously very quickly, again, we're only 10 miles wide, and we have this town here of Sylvan Grove, and we can tell, you know, we only have 2 miles to the edge of this snowband. So how do you communicate that to the next town over, you know, hey, you may or may not get 13 inches of snow in the next 4 hours? And I mean, that's something we really have to consider. And also, we have to consider our reports. And so this is this pink location right here was a very, very important reporting location. And I'll talk about that in just 1 second. But just keep in mind that this person here was also just a couple miles away from receiving 0 inches of snow. And so how might, you know, it kind of just goes to show like how important even one person and one spotter can be. So this is our first report of the day. It was for 5 inches of snow. And I didn't show it because I don't have time today, but we really were not expecting this at all. We had about 1 to 2 inches of snow expected throughout the entire day across central Kansas. So right off to get 5 inches, you know, so we're like, I don't know. So we start to call other people and spotters and dispatchers and see what we can come up with. And we're really not getting any other information and no other reports such like this to verify it. Well, within 45 minutes, it verified itself, as the same spotter is now reporting 9 inches of snow. So we're talking 3 to 5+ inches an hour, really, really impressive snowfall rates. But most importantly, we still have no other reports, and no other reports of accidents, anything, nothing at all. And so as users, we're still trying to figure out what's going on. Again, we're not expecting this. And just a few minutes after that, we have this tweet from another Kansas Highway Patrol. A nearby place just has 1 inch of snow. Another area in Salina, Kansas, where initially we thought this system was going to keep moving east as it had been all morning, completely dry without a flake. So we're still trying to wrap our heads around really what's going on. And so I'm going to turn it over to Chris now, and he's going to discuss kind of the science behind what went on this morning and how we can use satellite data to help determine that.
All right, can everyone see my screen okay?
Yes.
All right, great. I am Chris Jacob, and I'm one of the forecasters here / researcher of significant weather events here at the National Weather Service in Wichita. And I want to thank everyone at the Forecast Decision Training Branch for giving myself and Kelly this opportunity. And I'm going to be talking about the science for this particular event. And we'll start off with a quick science refresh of a few conceptual models, and then next we'll explore some mesoanalysis advantages of using GOES satellite water vapor imagery and a different product called the Advected layer precipitable product. And then we'll follow up with some science sharing and some of our findings from this February 25th, 2020 event. So, starting off, just kind of use your imagination. What phenomenon, as a meteorologist, what phenomenon could create this short-lived heavy snow band event with high impacts? If you were living anywhere or driving through this area of the snow band, you experienced 3 to 4 inch per hour snowfall rates, which was literally driving into a waterfall of heavy snow. So imagine traveling along the interstate 70, 80 miles an hour, and then you just hit this waterfall of heavy snow. Its mid-level frontogenesis is going to be the culprit, and we'll go through the science of it. So it's that mid-level frontogenesis plus low static stability that created this convective symmetric band of heavy, heavy snow. So looking at the science in our conceptual model from Emmanuel, we know if we have a weak normal symmetric stability, you kind of get this broad circulation of frontogenesis, but if the stability is weakened and you become more unstable, the updraft part of that frontogenesis circulation is contracted and enhanced. And what that does, it creates this narrow band, and your precipitation rates are going to increase, and usually the time scale of these narrow bands occur on a scale of 2 to 4 hours. So again, seeing that updraft portion of the frontogenetic circulation contract and enhance creates this very narrow snow band and those high precipitation rates. So how do we weaken that static stability using the science from this conceptual model? It's dry air. Bringing dry air in at the mid levels, typically from the dry conveyor belt, will steepen those mid-level lapse rates and destabilize things. And if you have a frontogenesis circulation going on, this just tightens and contracts that updraft portion of that frontogenesis circulation. So satellite water vapor imagery and conveyor belts. Ghost satellite water vapor imagery has many benefits for forecasters. The imagery provides good visual of these warm and dry conveyor belts in motion, which is great for anticipating important mid-level features like a developing trial airstream, moisture advection, and destabilization from the dry conveyor belt. In addition, because of this there's this strong relationship between potential vorticity representing those dark areas that you see on satellite water vapor imagery, you can watch those areas move and evolve, which are linked to areas of frontogenesis, changes in the static stability where it's weakened, and also jet stream dynamics. So this is something, and I want to provide thanks to Dan Bykos for sharing this advected layer precipitable water product and some of the loop images that he provided as well. This is a test product, and it's currently available for about 25 WFOs that receive this data in AWEBs via the LDM feed. We're one of those test products, or one of those test sites, and this product can be found online if you are not one of the test sites. That way you can evaluate and still utilize this product. So how this product works is it's water vapor imagery that is retrieved from the microwave instruments on several polar orbiting satellites. And since it's a microwave instrument, it can see through clouds, although precipitating clouds can still block the signal. There's 4 layers created from this product, and then the product is produced each hour, and it is mapped out onto a 16-kilometer resolution grid. It has an algorithm that takes most of the most recent polar orbiting satellite pass and then advects this moisture using the GFS model wind data. This product will then be updated with the next polar orbiting satellite pass. So let's dive into this event. Now that we refreshed our conceptual model of frontogenesis, I looked at the value of the advected layer precipitable water product, let's go ahead and apply it to this February 25th, 2020 event. So again, I want to thank Dan for supplying these images, and using this product for our frontogenesis conceptual diagram that's displayed down in the bottom right corner. You can visualize those areas of convergence, divergence, moisture areas, which gives us an insight towards a possible developing frontogenesis signal. And what I want to point out is those yellow areas and the narrow gap as you go from this layer, the 850 to 700, and as you go up in the atmosphere, notice how that gap is constricted. So what we're actually seeing, going back to our schematic, this is that frontogenetic circulation becoming contracted and enhanced on that updraft portion. And this signal showed itself, and you could see the trends once we jump to the next loop, about 2 to 3 hours before the band developed and impacted central Kansas. So as a mesoanalyst, once you see that happening, you can kind of get a better feel to be more proactive and say, ooh, there is a possible frontogenetic circulation developing, and it could make some changes to that band as it continues to expand into central Kansas. So here's the loop. And this is all the different layers. And I want to bring your attention to the lower left panel, because this is where the area was contracted and enhanced. Is watch this divergent area and convergent area. See how they kind of pinch together and converge? That's that frontogenesis circulation being intensified over that area. And again, this signal, you can see it happening and the trend of it narrowing 2 to 3 hours before the event unfolded. So that was a really good tidbit of information to go back and look at and realize, wow, that's kind of good information to have, you know, as a mesoanalysis and apply it to this event. So here we go, applying the science from the conceptual model diagram and PV. Because satellite water vapor imagery and PV anomalies, those dark areas on satellite, have this very good relationship. Looking at our schematic model here, wherever you see those dark areas on the GOES vapor satellite imagery, that represents weakening stability as the spacing between these theta E lines increase and the cyclonic spin is increased in those areas. So watch this yellow circle area. I'll put it in loop here and you'll see a couple PV anomalies or pulses, as I'll call them. They'll have this cyclonic curvature and circulation that were detected on the GOES water vapor imagery about 2 hours before that snow band impacted central Kansas in this area. So here's the satellite loop. And watch how that narrow snow band really narrows as the frontogenesis circulation becomes enhanced from the destabilization of that dry air in the mid-levels and the jet dynamics associated with those PV waves moving into that area. Again, this signal was detected about 1 to 2 hours before that band developed over central Kansas and really ramped up those snowfall rates with that constricting area of frontogenesis. So what we're looking at here, this is the anatomy of the heavy snow band. We're going to go back to start off at 6Z, and what you're looking at is the warm conveyor belt on the 290K surface. That's this green shaded area, and then we're looking at the dry conveyor belt on the 295K surface, and these are mixing ratios for those particular levels. And then we have our conceptual model of frontogenesis here. And as we walk through, I'll show you how changes happen and what it does to that heavy snow band. So here we are at 6E. Here's the radar imagery. We kind of have this broad frontogenetic circulation. The dry air is still off to the west, and you kind of look at the radar imagery and you see that it's not really narrow, just kind of a broadish band type area. So we're kind of stable right now. But let's jump forward in time to 10Z. And watch what happens. Now we start to move that dry air in over top that moist, warm conveyor belt. And notice I'll kind of toggle back and forth, and you can see what happens. Just in a span of 4 hours, that band starts to become constricted and more narrow as the frontogenesis is starting to intensify. Let's move forward 2 more hours here. And this is when it's starting to impact central Kansas between 10 and 12Z. So now the band continues to narrow even more as you bring more cold, dry air in aloft over top that warm, moist conveyor belt. So just kind of walking through, you can see the changes and the impact from that dry, mid-level cold air moving in over top that region. So now I'm going to run through it again, but this is going to be more of a 3D visual of the frontogenesis and the system motion, which actually played a big role. And what Kelly mentioned is when this band's set up, typically we expect it to move off to the east, but the system motion definitely played a role in this heavy snow band staying over the same area for a longer period of time. So I want you to use your 3D imagination as I paint this conceptual model from this frontogenesis snow band. So here's your theta E. This is your mid-level theta E. This is where your trowel axis would be on your 3D conceptual model here. And this was the system motion. It was kind of moving more south, southeast just paralleling that snow band, and this is the cold, dry air that moved in from the west over top that trowel axis, the warm conveyor belt. And what this did is it destabilized things and intensified that theta E gradient within that trowel axis. And now I'll overlay, and you can actually make a AWEPS procedure utilizing all this information. And now I'm going to throw on top the 700 to 500 advected layer precipitable water, and you could see that trend as well, the narrowing of that convergence and divergence area, also highlighting the potential of strong frontogenesis occurring over central Kansas. And here's a actual radar cross section from that snow band and the frontogenesis circulation that impacted central Kansas. So quickly here, if you like to use cross sections, I'm a big proponent of using cross sections. Kind of gives you that 3D visual of what's going on in the atmosphere. If we go ahead, take our PV anomaly, cut a cross section across, and you can notice this stratospheric downward motion or a trope fold response to this system moving into the area. And then if you overlay low values of EPV, this is highlighting CSI potential. And then you have the dendritic snow growth zone. So this is where your frontogenesis was really intense and amplified due to those lower values of EPV there in response to this tropospheric fold that developed over the area. And the system motion was key. If this continued to move eastward, the band would have been brief, but it pictured this trope fold coming straight at you and not shifting right or left. So that created a situation where the band remained stationary for 2 to 4 hours. So here's a loop here of the every 5 minutes where I have overlaid the dry conveyor belt, the moist warm conveyor belt, and the trowel axis, and the actual radar and satellite imagery all superimposed together. And you notice that the frontogenesis intensifies as you see that dry air spreading into the area. So it's really cool to get the visual of the science and our understanding of those conceptual models all coming together. And the great thing for a mesoanalysis is you can see this actually happening a few hours before the band develops over central Kansas. So you can anticipate, you know, that narrow band and the frontogenesis intensifying. So this is just about finished up here. This is a mesoanalysis procedure that we have at the office in our AWEPS, and this is what it looked like for that day, just to kind of give you a quick heads up of how you can utilize mesoanalysis during these winter weather events, just to get an idea of what's going on in the atmosphere. So some of the key takeaways is gradients in PV. This is where the action occurs. This is where your jets, steep stability gradients, tropopause folds all live in those dark areas. So kind of think of dark matter like on Star Trek. It's those areas that you can't sense with the normal sensors, but we can utilize our water vapor imagery and we could sense those dark areas, those dark matter areas, to kind of get a better idea of the hidden evolutions of what's going on in the atmosphere. Another great benefit of water vapor imagery is visualizing those conveyor belts, dry advection, and from the dry conveyor belt, which steepens those mid-level lapse rates, and then the warm moist conveyor belt, which transports that warm moist air. So the GO satellite water vapor imagery, the analogy I like to use, it's like using an MRI for PV in the atmosphere. It's so helpful because of that good relationship between those dark areas and potential vorticity in the atmosphere. And the advected layer precipitable water product is really good for diagnosing moisture transport, depth of moisture. And then as we saw in this example, it was showing some real good signals with the convergence of moisture and divergence of moisture becoming constricted in the verticals, showing that a frontogenetic circulation was probably occurring or getting ready to develop in that area. So what it all boils down to, the main key takeaway is we can apply this mesoanalysis science. it's not just a severe weather thing. We can also be proactive and utilize this during winter weather events. And I think I'm ready to pass it on to Kelly to finish this up.
All right, do you see my screen again?
Yes.
Yes.
Okay. So we have another about probably 5 or 6 minutes, if that's okay. Looks like we're running a little bit long. So we really wanted to, I'll try to speed it up a little bit. We wanted to really also kind of discuss the messaging and the challenges behind this particular event. And so we kind of have to look into our toolbox. So what do we have? We have all these advisories and warnings and different tools, but the most important one is going to be the one that gets people to react, right, and take action. So, I mean, we have the winter storm warning, which, you know, in hindsight, you know, the moment we reached for a winter storm warning that morning, but in hindsight, we think, you know, we didn't really reach the critical mass of people that really needed the information, which really were the drivers that were on the road that morning, because this did occur during the morning commute across I-70 and some other highly traveled roads. And we can kind of compare winter storm warning versus blizzard warning and compare and contrast what we have, but really it boils down to both of these options. They really did not have the WIA alerts or the wireless emergency alerts to really get the information in users' hands, but they did have the partner familiarity aspect, which is important when we talk about potential squall warning. So looking at a snow squall warning, you know, this event doesn't quite fit the conceptual model of a snow squall warning. You know, you think of a snow squall, quick hitting snow squall, you know, comes in, has some impacts and moves out, you know, in an hour you're done. And where this was more of a stationary, not a lot of wind with it, you saw how nice and stacked that snow was. But we also have another component to think about, is particularly to our office, that will our users understand this product? And thinking about that, we have never issued a snow squall warning from the Wichita office. And in fact, we just got the capability to do so last winter. And so you have to think, you know, if we put that out and someone gets a WIA alert to their phone, are they going to comprehend it the way we want them to and need them to, that this is a really intense scenario? But, you know, in hindsight, that's probably what we should have gone with, and that's something we definitely want to discuss further. And so just some other tools that we had, you know, at our disposal is obviously social media. But even then, when you're really trying to reach a driver, social media is not really all that helpful unless there's someone seeing the post and calling someone who's driving, or they happen to be weather enthusiasts, and so they get an alert every time we put out a post. And, you know, also people would have to be able to pick their location out on a map, which we know shockingly a few people are even able to do. So I just wanted to zoom back into a different location from this picture. And so let's just create a scenario where, you know, we have 30 miles between the town of Russell over here and the edge of the snow band. So let's throw a couple cars in the mix, and we have cars traveling 70 miles an hour on this highway during the morning commute, and they're going to come across highway that's got 5 to 9 inches of snow on it. I mean, yes, this is going to cause major problems, and that's what happened that morning. But what if we were able to use some of our partners' message boards or something, particularly at these 3 stars, at these 3 locations, are locations of message boards for the Kansas DOT. And we're actually able to work with them that morning and get those activated. So hopefully, you know, this poor guy driving this way who has no other way of getting alerted can see a sign that, hey, winter weather ahead, and maybe he pulls over for coffee or calls home or does something to gather more information so that they can make a better decision about whether to go forward or not. And we also have to think about all these drivers these days in this more and more digital world. We're not listening to the radio that is going to interrupt their music and tell them, hey, short warning, winter storm. You know, more and more people are listening to commercial-free satellite radio, or they're iPhones and apps and podcasts and you name it. So that's just something we always have to just be aware of when you're really trying to reach a driver. What is that avenue? And so even if we play the game of, okay, let's go with a polygon and a snow squall warning, well, how do we deal with that polygon? Is a polygon even effective for something stationary? So do we draw, the polygon like this, where we're just wrapping the system up? And, I'd kind of argue that, well, no, that's not very useful, because the people that are going to get alerted then are well aware that it's snowing over them. It's really the people outside of that area that we need to warn, especially when we're thinking mainly about the drivers in this scenario. So do we make a buffer around that polygon, around the snow band? If we can even discern where the snow band, how narrow it really is. And, thinking of cars, do we need to reissue this every 45 minutes so that the new cars coming into and closer to the snowband are going to get alerted? Otherwise, we're kind of stuck with, you either know or you don't. So I kind of just wanted to throw this up there. We have all these tools at our disposal, and sometimes they're going to have people take action and sometimes they won't, but we really need to figure out what the best combination of our tools are that will get people to take action. And sometimes those tools aren't our own, they might be our partners' tools. And we actually had a really good example of something positive in this case using the Pathfinder program. And via NWS chat, we were able to, once we really learned about this snowband and where it was, we were able to communicate that to Kansas DOT, and basically direct action followed that, and they were able to activate those message boards. So we have to hope, hopefully at least one person saw that and was able to make a better decision that morning. And so we kind of wanted to open this up, especially the messaging challenges, to especially also other offices that do use the snow squall warning and have public that is educated and they understand, what's the best actionable message in this scenario, with or without the education proponent, and what would you have done differently? And with that, we'll kind of end and open up to any questions. So thank you everyone for attending.
Thank you, Kelly and Chris. At this point, I will unmute everybody. And if you have a question or comment, just go ahead and feel free to speak. I believe you do need to unmute yourself if you want to speak. So questions or comments from anybody?
This is Scott. I'll just read a couple of comments from Sheldon. And one was pointing out that there was an inflection point in this. So it was rotating around something. So if you can identify that in your satellite imagery, that's going to help. And there's also a snowfall rate product that Sheldon sent a link to from GPM. It's on a polar orbiter. And the 934 UTC image highlighted this band. So it gives you a snapshot. And let me put the URL in the chat so people can look at that.
Okay, questions or comments from anybody else?
Yeah, just one comment with that snowfall eyeballing. It looked like the max snowfall rate was close to like 0.08 inch per hour snow water equivalent, which would have been close to an inch per hour at that 0934 UTC image time. You kind of have to give about a 30 to 45, maybe an hour lag time, because the microwave sensor is sensing snow or the snow water equivalent in the cloud. So that would have been a rate probably in the 10 to 11 UTC time.
All right, thank you.
Any other comments or questions? Brian has a question. Was the CSI strong enough to produce lightning? So was there any lightning with the event?
This is Chris Jacob. No, there wasn't any lightning. And typically when you get a CSI band development, you will not have lightning with it. It's not quite like convective instability where it's straight upright. This is more slantwise. It's an intense vertical motion, but it's not strong enough to create that charge separation where you'll start to get lightning.
Okay. Any other questions or comments?
Well, I'd just kind of like to, this is Chris again, I just like to thank everyone and hope that some of the science and everything that we showed and some of the visuals will kind of help people out, you know, because when we're faced with these winter weather events and stuff, is the wonderful thing of data infusion, displaying multiple products like water vapor imagery, radar imagery, all on top of each other, along with some high resolution model data. That gives us the best chance to be proactive, utilize the science to figure out what's going to happen. Because if you're just watching radar imagery, we're in a reactive mode. Then it's really hard to figure out what's going to happen and be proactive unless you throw those other ingredients on there of water vapor imagery and high resolution model data. We can build some wonderful procedures in AWIPS with that.
One other comment I'd like to make, I was looking at the Advected layer municipal water product, and for the time around the 12 UTC time, the precipitable water, if you totaled up the precipitable water at each layer, you come to about 13 millimeters per hour, which even though it's a very little amount of precipitable water, for a winter situation like this, it's an ideal amount of precipitable water that was being maximized for the event.
Thanks, Sheldon. Also, I'll quickly mention that ALPW is planned to come out over the SBN next year, but if you'd like to get it in your AWIPS and you don't have it, you don't want to wait till it comes over the SBN, just send myself an email, danbicus@noaa.gov, and we can get you set up with the LDM feed for that. Unless there's any other questions or comments, just give anybody a second chance here. We want to thank, oh, we got one more question. Brian, was a graphical nowcast issued for this event?
Yes, we did issue it. It was right after we got that first report, and we realized that, yeah, this thing was ramping up way more than what we originally thought. And we, Kelly and I, we were actually, both of us were working that morning, and we started ramping things up and quickly went to a warning and started making updates to all our products.
Okay, thank you. Any other quick comments or questions before we conclude? Okay, well, thank you, everybody, and particularly thank you to Kelly and Chris. That was a great presentation. If you have any ideas for future webinars, please let either myself or Scott know, and we can get you signed up to lead a future webinar. Thanks, everybody. Have a great day.
Thank you.